Hello everyone. In this video, we will dive into a groundbreaking man versus machine moment. The first time when a chess computer named Deep Blue defeated the reigning world chess champion Garry Kasparov during the revolutionary 1997 match. We will cover what exactly is Deep Blue, how it worked, how exactly it was able to beat Kasparov, and finally the impact of Deep Blue in the world of chess and beyond. Now, let's introduce ourselves to the historical context surrounding the match. Firstly, you may wonder who Garry Kasparov was. Garry Kasparov, as pictured in the image, was and still is seen as the greatest chess player of all time by many people. He was known for his aggressive playing style, where he led his opponents into tactically challenging positions and then outcalculating them to lead the victory of many games. So it was not long before he was able to become the chess world champion in 1985, at just the age of 22 years old, making him one of the youngest world champions ever in the history of chess. His domination continued, becoming the unstoppable world champion for 15 more years until 2000, when Vladimir Kramnik eventually dethroned him. Due to his dominance in the chess world in 1997, the Deep Blue team saw Garry Kasparov as a great opportunity to test the capabilities of their machine. If Deep Blue was able to beat Garry Kasparov, then it would be able to beat virtually any other human in the world. Now let's look at the other side of the match, Deep Blue. Despite being a computer, it was engineered through human skill and expertise. The Deep Blue team comprised of 3 core members. From left to right in the image, it had Joe Hone, the software engineer who developed advanced algorithms, Murray Campbell, who brought chess capabilities to the machine using his experience in playing chess, and Feng Xiangshu, the leader of the team who designed the core hardware technologies. Deep Blue was developed at International Business Machines, IBM, the biggest American computing giant in the late 20th century. This gave the team access to some of the most cutting-edge computing facilities, which made the Deep Blue machine powerful enough to defeat Garry Kasparov. However, Deep Blue wasn't created spontaneously. In fact, chess engines have existed since the 1960s, but the entire project originally started as ChipTest by Shu and Thomas Anantaraman at the Carnegie Mellon University in 1985. Shu was able to build custom chess chips to create a more efficient chess machine than some of the other machines at the time, while Anantaraman was the software engineer who developed searching algorithms. Although ChipTest was powerful, it was only able to beat players in amateur tournaments, not grandmasters or stronger players most of the time. Eventually, Campbell, from a rival chess computer team named Hitech at the same university, and others joined the team. Together, they developed ChipTest into DeepThought in 1988. They introduced more sophisticated algorithms, which we will look at in more detail shortly, with the sole aim of defeating chess grandmasters, which were then later refined in Deep Blue. To reflect this improvement, the name DeepThought was borrowed from the name of a fictional supercomputer in the book The Hitchhiker's Guide to the Galaxy by Douglas Adams, because it symbolized superintelligence and reflected DeepThought's intellectual ambition. Finally, Shu and Campbell joined IBM in the early 1990s, along with Joe Hone later on, while Anantaraman stayed at Carnegie Mellon to complete his PhD and go into his own area of research. Now, Deep Blue was born as a spin-off from IBM's nickname, Big Blue. Next, let's move on to how Deep Blue works in the first place. Here is Deep Blue's execution cycle. It represents what Deep Blue does while a chess game is going on. After the opponent has played their move, the move is entered into Deep Blue through a GUI interface. Internally, Deep Blue not only keeps track of the previous moves, but also updates its internal view of the chess position each time a move is entered. In the time allocated for Deep Blue to make a move, Deep Blue thinks carefully and tries to find what it thinks is the best move. We will dive into more detail on how exactly Deep Blue finds the best move shortly. Once Deep Blue has done finding the best move is displayed on a GUI system for a human to play on behalf of Deep Blue. Deep Blue doesn't have any robotic arms, so it cannot physically touch a piece of the chessboard to play for itself. The cycle repeats itself once the opponent in turn plays the best move until the game is over. You may wonder how powerful Deep Blue is in calculating the best move. Deep Blue is contained within a massively parallel system named the IBM RS6000 SP. SP stands for Scalable Power Parallel. Scalable means more chess chips can be added to the system at any time to improve its performance, while Power Parallel refers to its powerful parallel computing capabilities. Inside the system, there are 30 SP processors, one for each node. 28 of them have a clock speed of 120 MHz, and 2 of them have a clock speed of 135 MHz. Although the clock speeds are relatively slow compared to modern standards of several gigahertz, back in 1997, it was one of the most powerful supercomputers in the world. Inside each CPU, there are 16 custom chess chips of very large-scale integration, VLSI architecture, designed by Xu. VLSI refers to the millions of transistors found in each chip. In this case, 1.5 million transistors are found in each chess chip. As a result of all of this power, it can evaluate 200 million chess positions per second, far surpassing any other chess computer at the time, and you will see later on why this power is crucial to the success of Deep Blue against Garry Kasparov. This is where most of the magic happens. The image on the right shows what one of the 480 chess chips look like on the inside, revealing the inner circuitry powering the chip in the first place. On the left is all of the individual sections of the chess chip that allow it to find the best move. We will go over each section and find out how it helps Deep Blue identify the best move in any chess position. Let's start things off with the move generator. The move generator is a hardware system designed to generate all the legal moves of a position. When finding the best move, you always need the move generator because the best move must be a legal chess move that follows the basic rules of chess. The move generator itself consists of two internal components, the 8x8 array of combinatorial logic, where each cell represents a single square on the chessboard, and the finite state machine, both of which are implemented using hardware, for example, logic gates and transistors. You may ask why Deep Blue uses hardware rather than software to generate the best move? Well, it ensures that all the legal moves of the position can be generated simultaneously, as each square in the 8x8 array can be independently controlled, unlike in software, where the possible moves have to be generated one at a time in a slow, orderly fashion. This means less time is wasted, which is crucial in allowing Deep Blue to allocate more time in searching for the best move, rather than just generating the legal moves of a position. Each cell in the 8x8 array contains 5 parts. It has the piece register, which stores the type and color of the piece as the 4-bit binary number, the victim transmitter, which identifies other squares being attacked by the piece on the square by setting a unique piece ring that represents all the possible squares the piece can land on the chessboard, the attack transmitter, which identifies opponent pieces on the board that attack the square. It also sends rays like the victim transmitter, but the ray represents all possible positions of opponent pieces that attack the current square. The receiver, which coordinates all the signals to find the move and confirms legality of the move found. And finally, the distributed arbiter, which prioritizes moves and selects a move that goes into the finite state machine in descending order of priority. To prioritize moves, it uses a set of its own algorithms, and one such algorithm is the lowest valued attacker and highest valued victim algorithm. For example, prioritize attacking a queen over a rook, and prioritize capturing a queen with a pawn rather than with a knight. This particular algorithm helps in maximizing the material gain of a move. Now, which attack and victim transmitters are activated? Well, Deep Blue supports different move generation modes, and different attack and victim transmitters are activated on the chessboard depending on the move generation mode. For example, one such mode is All Moves mode, which activate the opponent's attack transmitters and my victim transmitters. The Checking Moves mode, which activate the opponent king attack transmitter and my victim transmitters, the Check Evasion Moves mode, and the Forcing Moves mode, which includes attacks, captures, etc. Once all the chess moves have been generated, the finite state machine is responsible for passing each move one at a time to the rest of the chip by receiving one move at a time as decided by the distributed arbiter. The way it does this is through a 4-stage process. Stage 1. It passes the move received into the rest of the chess chip. Stage 2. It masks the move using a 2-bit disable mask, which ensures the same move is not passed through the chess chip twice. 3. It pushes the move into the smart move stack, which is a fancy way of saying adding the move to the stack. Stage 4. It repeats until all generated moves are passed through or until it is told to stop passing through moves. Let's conclude the move generation section with an example. It is white to move, and our goal was to find moves that check the black king on e8, as I'm demonstrating the example of a checking mode. Keep in mind that I will show the example as if the process happens in sequence for simplicity, when in reality all of this process happens in parallel. Now the first step is to activate the find attacker transmitter from the black king. We do this by drawing unique outward rays, one for each piece type from the king that represent where the piece of the type has to be in order to attack the king. For example, the green circles marked in the diagram represent the outward bishop rays. The bishop must lie in one of these squares in order to attack the king. We repeat this process for the outward rook rays, marked in red, and the knight rays, marked in blue. From here, we can then activate the find victim transmitters of each of the 3 remaining pieces. We exclude the king, as kings cannot touch each other in chess, or else the position is illegal. To do this, we draw outward rays for each piece that represent the squares it can go to by drawing arrows this time, for clarity. Bishop rays are green, rook rays are red, and knight rays are blue, just like before. Finally, the receiver coordinates these signals by comparing the rays that pass through a common square. If the ray lands on or passes through a highlighted square of the same color, then the move is a legal checking move. For example, bishop b5, rook c8, and knight d6 are all checks. Next, using the lowest valued attacker system from before, the distributed arbiter then assigns a higher priority to any of the knight moves, knight d6 check and knight g7 check, because knights have less value than a bishop and a rook, and so one of the moves, let's say knight d6 check, gets passed into the finite state machine. And that's all there was for the move generation. Next up, we have the evaluation function. The evaluation function is a way of measuring how good or bad a chess position is. The idea is that if the chess position is better for one side, then that side has a greater likelihood of checkmating the opposing side. The function takes in a chess position and returns a number. If the number is significantly greater than 0, then the position is said to be better for white, and in this case, white is on the verge of winning the game. If the number is equal to 0 or close to 0, then the position is said to be roughly equal or exactly equal for both sides. It could mean that neither side is better than the other, or the game is a draw. Finally, if the number is less than 0, then the position is said to be better for black, and black would be on the verge of winning the game in this example. To determine which move out of a list of moves is best, lots of positions need to be compared with each other. The evaluation function provides a sensible way of comparing 2 positions, which cannot immediately be done by just staring at positions themselves. This allows Deep Blue to find good moves that result in more advantageous positions for itself. In this example, if Deep Blue was playing with white pieces, then Deep Blue would choose to play move 1, as it results in a higher score. The higher the score, the better the position is for white, and the lower the score, the better the position is for black. How does Deep Blue evaluate? Well, Deep Blue uses numbers, as computers love representing abstract ideas as numbers. In this case, Deep Blue calculates the evaluation of a position in centipawns, where the value of one pawn is 100 centipawns. You can also compare the values of other pieces compared to the pawn, assuming the pawn has 100 centipawns worth of value. The knight and the bishop are worth 300 centipawns. The rook is worth 500 centipawns, and the queen is worth 900 centipawns. Although in most contexts, knights are actually worth slightly less than bishops, but for now, we can say that both of them are worth 300 centipawns. A very crude evaluation function would be to just add up all the values of the pieces on white side and subtract it by the values of the pieces on black side. In reality, chess is a more complex game than just capturing pieces. Other factors need to be considered. For instance, king safety, activity of the pieces, location of the pieces, pawn structure, etc. These factors are known as positional factors. Deep Blue's evaluation function actually looks like this: a weighted sum of all of the factors or other features of the position it is evaluating. The weights control how important each factor is, which changes throughout the game. All of the individual scores of each of the n features are multiplied by the corresponding weights and then added together to get one overall score in centipoints. Deep Blue consists of two modes of evaluation, fast and slow evaluation, that determine which features of a chess position are examined. Let's compare which features are examined in Deep Blue. It depends on which of the two evaluation functions are used. The fast evaluation function is purely implemented in hardware to maximize the speed of evaluating positions. It consists of four main parts as shown in the diagram, and we go through them one by one as follows. Firstly, the piece placement section calculates the total material balance using the centipawn values for each piece, like I described earlier, while also considering where the piece is located. For example, a knight in the center will be worth more centipawns than a knight on the edge. Then, the game phase control, which is mainly responsible for adjusting the weights of the evaluation function depending on a game phase, such as the opening, middle game, or end game, and also produces bonuses for favorable piece combinations, for example, the famous bishop pair. Then, the endgame kingdom pawn array, which recognizes features of kingdom-pawn endgames. And finally, the endgame logic and ROMs, which recognize drawn and winning endgames. On the contrary, slow evaluation is much more detailed and has a lot more features to consider, over 8,000 of them to be precise. This time, it is implemented using a mixture of software and hardware, which gives flexibility for customizing the weights, as well as to add or remove some additional features to help make the evaluation function as accurate as possible. In the hardware implementation, each function has got several registers, where each register is responsible for highlighting certain features available in a chess position, if they exist, as well as assigning a score to each visible feature. Meanwhile, the software implementation uses lookup tables rather than physical register to retrieve scores of some features available in a position, for example pawn structure and piece mobility, that can be found in those tables. Overall, both the fast and slow evaluation programs are used in their own ways, and we will get into more detail on when the fast and slow evaluations are used once we get to the searching algorithm. So you may wonder if the evaluation function is a sufficient solution to finding the best chess move. While the evaluation function is a good measure for comparing how good different chess positions are, unfortunately, it is still insufficient in finding the best move. It doesn't provide long-term or even short-term strategy and checkmating ideas, which will have to be figured out by exploring a series of moves, rather than just looking at one position in isolation. A good way to demonstrate this is with an example. Look at this position. It is black to move, and using the material and even positional metrics, it seems that white has an overwhelming advantage because of the hugely dominating pieces that take over some of the most important squares on the board, while also seemingly attacking the more exposed black king. The white king seems to be relatively safe, tucked underneath two pawns on g2 and h2. So white should be winning. Boom! Plot twist. In reality, black actually checkmates white in one move. Queen f1 checkmate. Black wins. The point is, while evaluation functions are good at highlighting features about certain positions, it doesn't reflect how the position actually plays out in a real game. And this is where we move on to the final major component of the inner workings of Deep Blue that aims to solve this problem: the searching algorithm, which aims to introduce long-term strategic thinking that cannot be achieved from a static evaluation function. We could construct a game tree from a single chess position to represent every possible direction the game could take. For simplicity, I'll just show 3 possible branches for each position, when in reality most positions have up to 20 to 40 possible branches. Each branch represents a move from one opponent, called a half move or apply, which leads to the resulting child positions, represented as nodes. The game tree is what the searching algorithm will search on, and this is where short-term and long-term strategy will be introduced. Using the evaluation function we defined earlier in the video, the player with the white pieces would like to play a move to maximize the evaluation of a position, as a higher score means the position is better for white, while the player with the black pieces would like to play a move to minimize the evaluation of the position, as a lower score means the position is better for black. Chess is this constant metaphorical game of tug-of-war between the two sides, and to consider how good a starting position really is, it must consider the most optimal play, minimizing and maximizing from both sides. After this optimal play, it must then figure out what position will be reached and what the evaluation of that resulting position will be. This process is known as the minimax algorithm. We will look at a variation, or rather an optimization, of the minimax algorithm in more detail, known as the alpha-beta algorithm, which is used in Deep Blue search. Here, we have a simplified version of the chess game tree. Each chess position is represented by a circular node, where the color of the node determines which side is going to move next, and each half move is represented by an arrow. Execution starts by going as far down the chess game tree as possible until we reach the first node to evaluate, which is node 4. Let's say the evaluation of node 4 is +1. As we don't have enough information to conclude what the value of node 2 is, we need to move on to the next child node of node 2, node 5. Let's say the evaluation of node 5 is -6. As we went through all of the child nodes from node 2, we could determine what the value of node 2 would be. It would be -6 because black would choose the position with the lowest possible evaluation score. Then we need to find the value of node 3 in order to figure out the value of node 1, which is our end goal. But to do this, we need to look at evaluations of the child nodes, node 6 and node 7. Let's assume the evaluation of node 6 is -8. So far, the execution process has been exactly the same as the inferior minimax algorithm. Do you think we need to evaluate node 7? The answer is no, and this is where the process differs. We know that the value of node 3 would either be -8 or a value less than -8, depending on the value of node 7, as black would choose the lowest score. However, in either case, node 1 will always take the value of -6, regardless of the value of node 3, as white chooses the higher evaluation score all the time. Hence, node 7 is said to be pruned, ignored, and we find the value of node 1 is -6, with the best move being the green arrow labeled on the diagram. We did it. We found the best move. Here is the Python-style pseudocode for the alpha-beta algorithm described earlier. We introduced two new variables called alpha, representing the best possible guaranteed evaluation score white can receive, and beta, representing the best possible guaranteed evaluation score black can receive. You can see why this is called the alpha-beta algorithm now. Lines 2 to 4 detail on what happens once the bottom of the game tree has been reached. It returns the evaluation of each node using a user-defined evaluate function. Lines 7 to 14 calculate the value of node 1 by taking the maximum node value from the child nodes 2 and 3. In particular, on line 9, this uses recursion because to identify the value of child nodes 2 and 3, we need to know the values of the children of these nodes. The same thing occurs for the minimizing player, lines 16 to 23, except it takes the minimum value. However, the key thing to pay attention to is lines 12 to 13 and lines 21 to 22. This represents the alpha-beta cutoff condition which prunes a tree, for example node 7 from earlier. Finally, the function is called with alpha equals -infinity, best possible guaranteed score for white is the smallest possible value, and beta equals infinity, the best possible guaranteed score for black from the starting position is the largest possible value. We use a depth of 2 in our example, as there are 2 layers if we exclude the top, and the original position was white to move, so we set is maximizing player to true. One thing to mention is the importance of move prioritization. When we order moves from best to worst for the side, there is a greater chance for pruning to take place. This means the alpha-beta algorithm saves even more time when move ordering is added, and often the time taken to order moves is less than the additional time taken for the search if the moves weren't ordered properly. This is why the distributed arbiter from earlier was necessary for the move generation. As a result, the alpha-beta pruning can search up to twice the depth of the game tree compared to the standard minimax algorithm in the same time, with the best to worst move ordering system in place. However, the alpha-beta algorithm has a major issue. It can be very computationally intensive to search through lots of positions at large depths. The number of positions to evaluate grows exponentially with each depth. Given that each position has on average 30 legal moves, the number of positions after each move, one for white and one for black, increases by a factor of approximately 1,000 times each time. Claude Shannon's estimates on a table show how many positions are there to evaluate in even just 5 moves. These huge numbers emphasize just how difficult it is to search through large numbers of positions, which is why optimizations like alpha-beta pruning are essential. Typically, a larger depth is preferable because if Deep Blue can see more positions, Deep Blue can find more winning opportunities to take advantage of. Hence, there is this trade-off between speed and accuracy, which is a problem in time chess matches like this one against Garry Kasparov. Luckily, the Deep Blue saw all these issues coming, and that's why they implemented the alpha-beta algorithm using parallel architecture. Deep Blue implemented a parallel architecture with 30 powerful processors for this exact reason. It is to allow different processors to work on the same tree at the same time. As shown here, one of the SP processors is the master processor. This processor initiates a search and coordinates the activity of the other processors. It searches the first few replies of the game tree to find promising positions to evaluate using a slow evaluation function for accurate elimination of poor candidate or rather leaf positions at the bottom of its tree. Then, it distributes these promising positions to each of the 29 other worker processors, which will go even deeper using a mixture of the fast and slow evaluation functions. Finally, the remaining promising positions that they are left with after analysis will be passed to each of the 16 chess chips for a rapid hardware search using a hardwired fast evaluation function to quickly recognize different positions on millions of potential candidates. All of this means that deeper layers of the tree are evaluated in parallel, increasing the efficiency of the search. As a result, Deep Blue can evaluate up to depth 12.2, seeing around 6 moves ahead on average in 3 minutes, evaluating approximately 1.41 billion chess positions in that time. Due to limitations in Deep Blue's search depth caused by the computational complexity of the algorithm, the Deep Blue team also incorporated something known as the Opening Book inside Deep Blue. The Opening Book is a software database containing around 4,000 chess positions that acted as a guide for which opening moves to play. For example, the Opening Book contained lots of positions in the Sicilian defense, which is one of Kasparov's favorite opening in his repertoire for World Championship matches and other tournaments. In each position, the Opening Book would tell which move Deep Blue should play without Deep Blue needing to evaluate chess positions. This helps address a fundamental limitation of a limited search depth. Opening and middle game evaluations are likely to be incorrect because it takes many more moves for Deep Blue to see the consequences of playing a move in a position compared to an endgame position. You may wonder how does Deep Blue move through the chess tree in the first place. It is the smart move stack that allows this to happen, as an essential part for the hardware search and the final component in the chess chip. The smart move stack itself consists of 2 parts, a regular move stack and a hardware repetition detector. Fundamentally, it operates via a last in, first out principle, meaning that the latest or most recent move pushed to the stack, added to the top of the stack, is the first one that gets popped, or rather removed, from the stack. Due to this last in first out property, it makes it incredibly useful for searching through each layer in the chess game tree. For example, to get to board position 4, we could push move A and then move C to the stack. Once we have finished evaluating board 4, we need to go back to board 5, and we can do this by popping the stack and then pushing move D to the stack. Meanwhile, the hardware repetition detector uses a buffer, an area of memory, to store the last 32 moves of a position, which detects how many times a position is going to repeat and when a position is about to repeat. This is useful for enforcing draws by intentionally repeating 3 times as shown to obtain a draw by threefold repetition, as well as avoiding draws by avoiding repetition depending on the situation. In summary, all of this information is pretty much how Deep Blue works. To summarize, Deep Blue is a huge parallel system with 480 custom chess chips, 16 of them per SP node. The sole aim of Deep Blue is to find the best move from any chess position, and these chess chips allow Deep Blue to do that using a move generator to generate illegal moves, the evaluation function to score a position based on how good or bad it is, the searching algorithm which introduces strategic thinking, and a smart move stack, which stores moves used in a search and detects repetition. Now let's let's dive right in to the 1997 match. The 1997 match was the second match between Garry Kasparov and Deep Blue. It was a rematch from the previous 1996 match in which Deep Blue lost. Like the 1996 match, the 1997 match consists of 6 games where each side has 2 hours to play the first 40 moves and then an extra 1 hour to play the rest of the game after move 40. The winner of the game would receive 1 point while the loser would receive 0 points. If the game ended in a draw, then both players received half a point, and whoever had the most points at the end of the 6 games won. Tension between the two opponents had been mounting, with plenty of spectators and reporters observing and broadcasting the game from a distance. Only time could tell who could win. While Kasparov typically plays more aggressive openings like the Sicilian defense, Kasparov purposefully played more solid strategic openings against Deep Blue to try to exploit one of the key weaknesses of Deep Blue: long-term strategic play with hidden and obscure ideas. He also tried to avoid as much of the opening book preparation as possible by playing rarer sidelines rather than main lines. For example, in Game 1 against Deep Blue, Kasparov played into an ultra-quiet variation of the King's Indian opening, involving a lot of maneuvering. Kasparov was playing some slow, steady, non-confrontational moves to wait until Deep Blue makes a significant mistake in the middle game, with which he was able to take advantage of. He aimed to win with white and draw with black, which mostly happened during the 1996 match. We will go over 3 games in more detail: games 1, 2, and 6. In game 1, Kasparov played with the white pieces while Deep Blue fought with the black pieces. In fact, his strategy worked for game 1. Kasparov played very solidly, targeting Deep Blue's weakness of the f5 square while Deep Blue recklessly exposed its own king. Eventually, Garry Kasparov was able to successfully break through with the 30th move, pawn to f4. This made Garry Kasparov lose a rook for a minor piece, seemingly going down material. However, once the sacrifice was accepted by Deep Blue's position began falling apart, as the 2 passed pawns were very close to promoting. Eventually, on the 44th move, it played rook d1, which didn't stop the pawns at all and was apparently caused by a computer bug. After 45g7 was played, it resigned. This game illustrates another problem with searching algorithms. If a limited depth is used, then Deep Blue cannot evaluate consequences of seemingly good moves in future positions beyond its search depth. This is actually known as the horizon effect in action. However, the Deep Blue team learned from their mistakes and fine-tuned the searching algorithm, eventually leading to Deep Blue's comeback on the very next game. This time, Deep Blue played with the white pieces, while Garry Kasparov played with the black pieces. Although this game started as a solid Ruy Lopez opening, Deep Blue was able to apply a lot of pressure to Kasparov's queenside by threatening to open the A file by capturing on b5 in order to invade Black's position. Meanwhile, Black's pieces are mainly restricted or stuck on the A rank, being quite passive in the process. This eventually led to a pivotal moment on move 36, when the pawn on b5 was finally captured. However, this move was controversial because Garry Kasparov expected a different move to be played: queen b6, as shown by the red arrow. The idea is that queen b6 will win a pawn on b5 by force after the bishop was guarded. This means that Kasparov will expect queen b6 to be played, as engines at the time preferred material over long-term strategy. But Deep Blue played a takes b5 as a prophylactic move to shut down Black's counterplay. At the time, he accused the Deep Blue team of hiring a grandmaster to play the move instead of the computer, because it was such a grandmaster level idea. But in 2016, Kasparov admitted in an interview that he takes back the cheating allegations on what happened during the game. In the game, though, Deep Blue was able to invade on the queen side, while Kasparov couldn't fight back on the other sides of the board, leading to his resignation on move 45. Interestingly, the controversy doesn't stop there, though. Kasparov had one last fighting chance with queen e3 to go for a draw by perpetually checking White's king, which could have saved the game for him. Games 3, 4, and 5 all ended in draws. The next, and probably the most exciting moment of the match, occurred in the tension-filled Game 6, the shortest game in the entire 1997 match, lasting only 19 moves. Like in Game 2, Deep Blue played with the white pieces, while Garry Kasparov played with the black pieces. Kasparov played a relatively solid, but also common, Caro-Kann opening to try to clinch a win in the last game. However, things quickly backfired when Kasparov played a very risky move, h6. This allows Deep Blue to play a powerful sacrifice, knight takes e6, as marked by the blue arrow, which significantly weakens Black's position and makes Black's king more vulnerable to attacking opportunities. However, Kasparov admitted that he played this move on purpose because he didn't expect knight takes e6 to be played at all. But unfortunately for him, this position was found in the opening book, so Deep Blue knew what to do without even having to search. Eventually, Deep Blue was able to win Black's queen when Black's weak defenses were overwhelmed, and eventually broke through with the move c4, stripping away the defensive purpose of the b5 pawn, as well as attacking the exposed king. Kasparov resigned on move 19. History has been made. Deep Blue wins by a 1-point margin, 3.5 to 2.5. Machine defeated man. To conclude this video, we will briefly look at the impact of Deep Blue. The win was not just a symbolic victory, it drove decades of human progress in the 21st century. While Deep Blue is no longer functional, IBM used similar parallel computing technologies in Deep Blue to develop more advanced parallel computing systems, such as BlueGene, which became the greenest supercomputer in 2010, and Watson, which specializes in natural language processing, a form of machine learning and artificial intelligence. In chess, modern chess engines have emerged, like Stockfish and Leela Chess Zero, which use machine learning algorithms alongside brute force search to evaluate chess positions much smarter than Deep Blue ever could. Beyond chess, the core parallel computing technology in Deep Blue is used to solve complex financial modeling problems, is used in data mining to spot patterns in huge databases, and even is used to develop new drugs in the pharmaceutical industry. That brings us to the end of this video. Thanks for watching. And here is the bibliography.